Hello. Hello, everyone. Good morning. My name is Maxim. I'm a software developer. I write in different languages like C, C++, Go, Python, and so. And you can find me on the internet by the nickname cdump on Twitter, GitHub, and XCOM, and Telegram, of course. And today I'm going to talk to you about control flow graph. I will present my new algorithm to reconstruct control flow graph from EVM Bytecode. I will overview existing tools. I will show you how I benchmark them. Of course, I will describe my new algorithm, and we'll talk about my EVMole open source library, where I implement this and some other algorithms. And if we'll have questions, time for questions, there will be question sessions. So here is a basic contract. It's not ERC20, but some simple contract. If we compile it with Solidity compiler, all we can see is the binary of runtime part, which is just pairs of bytes, and we can decompile it. So basically like 6080, it's instruction #1 80, and so on. This is like a one-to-one mapping, just like written in the Ethereum yellow paper. And I need to give you some definition, like a basic block. Basic block is continuous. So you can read this definition, but I can say it in the other words. Basic block is a set of instruction, such if we execute first instruction block, we will definitely execute the last instruction block. So it's block without any possibility to break through execution. And we can use this definition to break the decompiled output of previous code to these basic blocks. As you can see, we can break on jump, conditional jump instruction, or the revert instruction, because this instruction, by the definition, breaks the block execution. And if we combine this basic block with edges, like how can we go from which block to which, we can get the basically control flow graphs. Like basic blocks with edges, and you can see like more than one output edge from some blocks, because it's conditional jump. We have a true branch, we have a false branch, and so on. So some different tools exist to reconstruct control flow graphs from EVM bytecode, but all they have the same problem. I can repeat myself from the previous FCC presentation. We don't know how accurate are them. We don't know which one is better. We don't know, we know that they works in some kind of way, but we don't know exactly how. So the first part which I did is introduce benchmark algorithm. It's not so easy like for the selectors or some other stuff which I can just ask to Solidity compiler to output. So the ground truth is not easy to get. So here how I solved it. By the definition, a basic block is continuous subsequence of EVM opcodes, and we can filter out definitely unreachable blocks. Usually, it's just a metadata in the end of the contract, but sometimes old compiler produce more definitely unreachable blocks for especially early versions of Solidity compiler. And after that, we can set definition. We get set of basic blocks, set of all basic blocks after initial partition and removable invalid blocks, and the set of blocks which some algorithms produce after control flow graph reconstruction. And we can now get false positive and true positive. Oh, sorry, false positive and false negatives. And we can compare algorithms by this matrix. So false positive, by definition, it's a set of control flow graph blocks minus the set of basic blocks, and should be empty in correct analysis, because if some control flow graph reconstruction algorithm produce block which we definitely know it cannot be reached, then it's totally a false positive. With false negative, it's not so easy, because it may include like dead code, but we can assume that a fewer indicates more precise analysis. And here is the results of this benchmark algorithm. You can see EVMole, where my library, where I implement my algorithm, outperforms all other solutions in a number of basic block reconstructed, and the false negative also the lowest. And by the way, the time which EVMole uses to produce these results, it's only 30 seconds, and the second place itself use 40 times more time to get worse results. So now I will describe my algorithm. As I said before, if we have basic blocks, we need to get edges from how can we get from each basic blocks to another. And this is trivial case, because here is conditional jump, and of course we always know the false branch because it's fall through, and for the true branch in such good cases the destination is pushed to the stack in the same block, but in this situation even in the previous instruction. So it's trivial case to get the true branch conditional jump destination. But for some other blocks, like you can see on the right, basic block consists only for swap and pop and jump instruction, and we cannot. So we need to analyze previous, like parent blocks, to get the possible destination of this block. And to get it, I introduced stack analysis. Like when we enter basic block, we have a stack which is produced by the previous block. We can mark it like before 0, before 1, before 2. This is results from the previous basic block. And we know for every instruction how many stack elements it consumes, how many stack elements it produces. And we can execute some basic instructions like pushes of a constant, some basic math operations. And after that, we can get the new stack, like symbolic stack results. I can show you an example. If we have this before, after the swap operation, we have this. After the swap one operation, we have this. After pop, you have this. And finally, we have this. You can see that the first element of the stack didn't change, and it only removes two stack elements. And if we see a more complicated example, and we have all stack analysis for each block, we can start to combine them. Because you can see on the right side that it's still unknown for the last block. It depends on the previous, and some depends on the previous, but we can combine them because as you can see, like before 0 now becomes before 2, because we take the first element of the previous stack and so on. By combining them, all that, we can explore our parents block and get the final stack, symbolic stack result. So in this example, you can see that the last block jumps to something which is before 2, and the stack result for the parent block is before 2 element is before 1, so we need to jump to before 1 of a parent block, and so on. So basically, algorithm is recursively explore all parents until we find definitely jump destination. So we find the output destination of this block. Repeat that all until all unknown jump destination are resolved, because some are already resolved, as I show you in the first slide, where the jump destination is trivial, like it's pushed to the stack in the same block, and get the profit. But actually, this is how this algorithm looks like, simplified version. So basically, we have hash map of all parents, which we pre-compute. We have stack element at position for each block, which we also pre-compute. And we can resolve these parents, which I show you for slides earlier. But the first problem is cycles, because a node can be visited multiple times, and unlike typical graph traversal algorithms, we cannot just introduce a hash set and never visit this node again if you visited it before. So I introduced one another thing which I called intermediate states. If we visited this block and the result of the symbolic stack is completely the same, so we can hash the stack sim. That means if we go around, we will definitely go out to the same destination. So we can break our execution here, because we definitely know that we will never see any other outcome, no matter how times we visited this block. And this is how I check it in the code. And after that, I anyway need to limit the total number of operations, because some contracts are very strange contracts. So I analyzed all mainnet contracts with my algorithm. It's about 1.5 million. It's all analyzed in 15 minutes on 24 CPU cores, and only like free contracts. It's less than 1 person are affected by the limit, so it's fine to introduce this limit. And then another part of my algorithm that if my algorithm don't know the result is certainly, if it's uncertain, it will explicitly indicates it with option. This Rust code, so I can see I don't know how to the destination of this block, so I'll just say it's none. And this is how results from my algorithm looks like. The block starts at this pointer, extraction pointer ends here, and for the jump, it's a jump to the predefined destination. For the conditional jump, we have true and false branches destinations. And in dynamic jump, if the jump destination depends on the path how we came to this block, then I produce, like if we came from this node, then we go out to this node. It's similar like a phi function in SSA analysis, if you want to know. And what makes my algorithm unique? It's bottom-up analysis, so I'm not trying to go from top to bottom, like from entry point and analyze everything. I'm trying to go from bottom to up, and so only part of the actual blocks are analyzed, which decreases the total time of analysis. It avoids path explosions, because I track nodes which I visited with with symbolic stacks, and advanced loop detections. As I said before, I introduced this algorithm in my open source library. It's called EVMole. It's available in Rust, JavaScript, TypeScript, and Python. It's fully open source. And you can visit it on evmole.xyz. This is a demo of using this library. Besides the control flow graph, it can get you selectors of the functions, function arguments, state mutability, storage, usage, and now it's get basic blocks and control flow graphs. And this is how it looks like. So you can just put contract address, you can input the contract deployed bytecode, and then you have tabs with function, storage, disassembled, and control flow graph, which is totally interactive. You can play with it, you can move it to try and understand the contract logic without source code of this contract. And again, this is sources on GitHub, this is demo website, this is QR code to the demo website, and I think we have some time for questions, if you have one.
Yes, I see.
Thank you.
I have a question. Did the compiler optimization introduce any difficulties to your algorithm?
Yes, of course, but I say that the modern version of Solidity compiler are better than the older versions, because in older versions there's a lot of strange logic, like a lot of dead code, and I don't know, is it a dead code or is it my algorithm failure? So I need to review it with my eyes, so I review all errors. But of course, all these dynamic jumps, it's introduced by compiler, because if you run compiler without optimization, probably it will get you like straightforward code without so complex logic. But as I said before, I analyzed all mainnet contracts and everything looks good. So only small portion of all contracts didn't. So some contracts break my tool, but it's very small number of contracts.
Okay, sounds great. Yeah.
Thank you for the question. Yep.
Hi, I think in the beginning of the talk, you said yourself that there are possibly different ways to represent the CFG. And if we use the different tools, I think they might generate a slightly bit a different kind of CFG. So how do you approach this problem, and how do you compare your algorithm with other tools out there?
Yes, the same as I use for the, as I said before, my tool also extracts selectors, arguments, and I compare with other tools the same way. So I packed other tools in Docker and then write Python script to pre-process the output to match the exact format. Like maybe 50% of the programs, like other algorithms, output in the same way, but for the other half, I need to do some pre-processing, but anyway, I can get the like common part, the total number of nodes, the nodes entry point, exit points, and so on. That's how I compare it.
The connections are more tricky.
Yeah, connections are more tricky. That's because that's why I only count the total number of reachable nodes, which is easier to get from all of its tools.
Thank you.
Thank you for the question. Is there any more question? Please raise your hand. Okay, no more questions. Thank you for the speaker.